Hello everyone. Um, so I want to talk about Boussinesq hypothesis for this one. Okay. Just before we start, here's a quick prerequisite. Before we begin, it's important that the reader does not confuse the Boussinesq hypothesis, or it is sometimes referred to as Boussinesq approximation regarding buoyancy-driven flow. Okay. Um, if you are here for that, see other sources. Okay. First of all, there's books. Yeah. This book is great. Yeah. The finite volume method briefly talks about it. Introduction to Fluid Dynamics by David something talks about. Is it David? Yeah, I think it's David something. It's a very old book. It's got a picture of a jet and it's great. Talks about Boussinesq approximation for buoyancy-driven flow. And I like learning from videos, so I personally recommend Fluid Mechanics 101, taught by Dr. Eddy and Winhurst. A seriously great 30-minute video on Boussinesq approximation for buoyancy-driven flow. Alright, let's get started. Okay, who was Boussinesq? First of all, well, Joseph Valentin Boussinesq was a French mathematician, physicist, okay, scientist, the whole trifecta. Okay, he worked heavily on fluid dynamics, hydrodynamics, and he had some great contributions in thermodynamics, where heat flow in a pipe, is still in the fluid dynamics range. Okay, and mainly the friction parameters that fluids go through in a pipe, all that stuff, all that jazz. Yeah. So now, one great and main contribution he made was the solution of the product of two averaging velocity fluctuations. It's a mouthful, but I'll show you what it is in the RANS. I shouldn't have put simple because it's not simple, but in the RANS, one equation and two equation turbulence models. Okay. Before we start the super details, let's build the foundation first. Okay. As mentioned in the previous paragraph, RANS, or Reynolds-averaged Navier Stokes equations, are a set of equations to determine fluid properties using the finite volume / finite element method. Yeah. So ANSYS and OpenFOAM use the finite volume method. Okay. In RANS, the fluid properties such as velocity components, temperature, etc., can be broken down to two separate components, like shown in equation 1. Yeah. So you've got the mean and you've got the fluctuating. Okay. The sum of this will get you the original variable. Okay. Phi, I've said phi. Treat phi as anything you can think of. Okay. It's a dummy variable. It's not very important for this to know. To know what variable it is, just take the principles behind it. Okay? We actually call this Reynolds decomposition. Okay? Any instantaneous variable, okay, can be broken down into two components. I want to iterate this: the mean and the fluctuating. Great. Now, there are rules to Reynolds decomposition. F bar bar is equal to F bar. Okay? I want you to think of a series. This should be quite intuitive, but let's say you don't understand this. I want you to get a series. Yeah? I want you to sum up the series and find the average. Okay? Now, I want you to, with the solution, I want you to find the average again, just with the solution. Yeah? And you will get the same answer. Yeah? That's what all it means. Okay? The second equation is what I would call the linear operator rule. Yeah, it just basically means the averaging can be broken apart. Yeah, as long as it's a plus or minus. That's all I say. Third rule is an important one. Yeah, it comes up a few times. Basically, it just says that the averaging or fluctuating component is 0. Yeah, you just have to plug it into the original equation. Okay. F bar minus F bar bar over big bar is F bar minus f bar bar, yeah, f bar minus f bar equals 0. Anything times itself is 0, okay, basically put. Or I like to think it as a quick way for me to remember it. It's technically wrong, but you know, it works for me. What's the average of a sine wave, yeah, of a simple sine wave? So if you go in decimals, type in y equals sine x, find the average of that, it's 0, okay? So it just means the average of a fluctuation is 0, okay? This is basically saying that the bars can be broken up, yeah? It's still the average, it's just, instead of big bar, you get 2 small bars, yeah? F bar times G bar, okay? We know that F, fluctuating component bar, is 0, therefore this entire thing is 0. Oh, yeah, very simply put, okay? This is a very important rule, actually. So, time averaging has started, yeah? This is the original equation. You started the time averaging, put a bar at the top, okay? Put this in, F bar plus F prime times G bar plus G prime, yeah? Using the claw method, multiply it out, yeah? And you will get this. Remember, these will go to 0, okay? Because of this rule, yeah? And you'll get this. Now, these two rules, personally, I haven't seen them that much, but they do come around some often in some cases, but basically it just means that the averaging can be brought into a derivative, yeah? That's all I'm saying. And the averaging can be brought into an integral, okay? Okay. Now, when you're dealing with any fluid property, guess what? You're dealing with the $1 million question, that is the Navier-Stokes equation, okay? Yeah, I'm not sure if the viewer is not aware of this, but there is a 1 million prize if you can solve this equation, okay? The millennium question, or the millennium equation. I can't remember, but it's one of those. Anyway, basically, this is the Navier-Stokes equation, okay? I think mathematicians will see it more like this in this method. Oh, I also want to add that I have given it in indice form, okay? Or, to be more precise, Einstein indices, Einstein summation of indices notation. Basically, it just means that I and J can be 1, 2, or 3. Yeah, UI is X, U2 is V, U3 is W. Okay, so U is in the velocity component in the X direction, V in the Y direction, W in the Z direction. Okay, but yeah, I've just given it in indice notation. Now, I think I'm aware and truthful when I'm saying mathematicians will see it in this format, you know, from a more physical and mathematician background, while engineers will see it in this format. It is a little bit more compact, but here for us, speaking as an engineer, this is we see it as stress. Yeah, this is, you have to notice this is actually a stress component. It has the same, it's pascals. Yeah. Because as engineers we deal with stress a lot, you know, especially in undergrad. When you learn structural mechanics, you learn about von Mises stress and normal stress, shear stresses, and blah 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 blah. You know, yeah. Okay, that's it. So that's the Navier-Stokes equation, yeah, for in engineering and in indice format. Okay. Now we apply Reynolds decomposition for the left-hand side on the second term. Basically this time, I would recommend you to apply Reynolds decomposition for all the terms. Okay, it's a nice little exercise. It will take a page or two, but it's a nice little exercise. But the problem when you're trying to solve it in CFD, the problem is this. Yeah, it's this term. I'll show you why. So this is the term. Yeah, I've taken a row out. I've said it's incompressible just to make life easier. I said rho is incompressible. Okay, applying the product rule. Look at the row out outside the derivative. Time averaging has begun. Okay, we plug in the averaging component plus the fluctuating components. for I and J. Okay, do the claw method, yeah, and you'll get this. Okay, do it, you should get it. Okay, if you don't get it, please go back to this rule, and you should get it. Okay, if you don't get this, then I recommend you to start from the very basics, learn from expanding brackets. Okay. Anyway, it's nice to go back to the roots of mathematics. You know, it's very helpful. Okay. Let's talk about now. Let's think. Now, put your engineer hat on. Okay. We had take off your maths hat, put engineer hat on. When you think logically, this is pretty straightforward to solve. Okay, this part. It's just basically ui, uj, the product of those, and average it. Yeah, it's very simply put. It's just that. Okay, and it's straightforward to solve, so not a big problem. This is what kept up Boussinesq up at night. Is this, the tail end of the equation? Okay, because it's not zero. Yeah, it's not zero. It cannot be zero. Yeah, because that means the instantaneous value is zero. Okay, because we've broken it down. Okay, so it's not zero, and you have to remember that it's like the BODMAS, you do the fluctuating part first, then the averaging. Yeah? So times fluctuation times fluctuations. Okay, it's being multiplied, so it's not zero. Now, Boussinesq, like this, this is the part he was trying to solve. Okay. Now, also want to mention, this is like one of the key things. I want you to do dimensional analysis for this. Okay, I'll come back to it. Pause the video. Do dimensional analysis without the row. You'll see why. Okay, I've given a little quick hint here. It's TKE. Yeah, it's TKE, and I think this is one of the hints that gave Boussinesq, saying, "Oh, this is turbulence in there somewhere." Okay, but before we start, sorry. Boussinesq comes along and he spends time on this problem, a considerable amount of time, I should say. His empirical testing show that there is some commonalities between laminar and turbulent stresses. Yeah, this is laminar stress you'll find in laminar flow. Okay, if you did a fluid dynamics class, you're well aware of this equation. You should know it off by heart. Okay, yeah. So his hypothesis states that turbulent fluctuations have a dissipating effect on the mean flow. Okay? In terms that we can understand, as engineers we can understand, this means that there's a linear relationship between the turbulent flow stresses and the mean stream rate. Okay? If the flow is isotropic. Now, it's actually one of the reasons I made this video. A lot of people did not stress this parameter important enough. It only works if the flow is isotropic. Otherwise, the whole hypothesis breaks. Okay, and I'll come back to this. Okay, basically, it just means when the magnitude of the components are the same in all directions. Okay, very simply put. That's all it means. So, but he said there is a commonality between laminar and turbulent. Okay, he said, let's add some stresses. We need to add some terms. One term that we need to add is definitely TKE. Yeah, there is an effect here. There is a TKE. There's turbulent kinetic energy. Yeah, because if you do dimensional analysis, you get M2, M squared divided by S squared. Yeah. So this is his hypothesis right here. Mu T. Yeah. Nu T, not mu, nu, T, the turbulent kinematic viscosity. Okay, that's what it means. And you got the TKE here. Okay. Now, and yeah, that's his hypothesis right there. In incompressible format, and incompressible, and in the compressible flow regime. It's this, yeah. Instead of bringing the rho to right hand side, we still stay on the left. Yeah, there's a row this side, don't worry about it. The units are conserved. Okay, now I want to iterate. Okay, this is such an important part when I'm teaching students, when I'm tutoring them, engineering students. They, especially the undergrads, they do not understand the concept of a turbulent property. Okay, when they do the derivations of this, they always forget the t, and I end up screaming at them because this is such an important parameter. Now, I want to tell the viewers the turbulent kinematic viscosity is a turbulent property, not a fluid property. It changes from one point to another. Okay, it's so important that you remember that. Yeah, and people from these two references find that it's actually heavily affected by flow history. Yeah, so it changes so much. Yeah. Okay. Now that's it. Yeah. I also want to mention that the reason why this term is not an incompressible one, this term, yeah, this derivative is actually SKK. It's the same term. Yeah, we know SKK is equal to 0 in incompressible. So this term goes away in incompressible. That's why you don't find it. Yeah, nice little hint. So if you have to remember this, remember the whole thing. Yeah, no, I don't think in any exam you have to remember the entire thing. But it's nice if you can remember like this, and you know that this is Boussinesq hypothesis here. This is some stress. This is pressure. And this is the moment equation. Yeah, that's it. Now, for the one equation model, Mr. Prandtl come along, Ludwig Prandtl, Austrian or German physicist, I can't remember, came along and he introduced Prandtl mixing length concept. Okay, that's used for the one equation terms model. I'm not a big fan of that model. There's quite a lot of errors to it. Anyway, the one model that I am familiar with, and I think most of you guys are familiar with, are the two equation models. Yeah, K epsilon and the K omega models. Okay, the K omega models have a different way of finding ut. Okay, but in the K epsilon model, it's actually the ratio of TKE epsilon some constant, which is 0.09 after empirical testing, and density. Yeah, it's just turbulent dissipation. My bad. Yeah? Turbulent dissipation and density. Yeah, of the fluid in action. Then we can solve for this. Yeah, because we didn't know how to solve for that, so Prandtl came along, introduced this, and after a while, other people find out this can be applied for two equation models. Yeah. Now, there is some uses and limitations. Okay. So let's talk about the positives. This Boussinesq hypothesis is very good. Boussinesq hypothesis is very good in simple shear flows, pulsating jets, subsonic fluid properties, and mixing layers. For this one, this is a caveat situation. Yeah, I find that for my student and not for my students, from the people I worked with, one guy was dealing with Mach 3. Yeah, Mach 0.83. Yeah, Mach number 0.83 over Naka airfoil, and he found that K epsilon model was just the eddy viscosity was way off, and the fluctuations were way off. The turbulent Reynolds number was way off. So if the turbulent Reynolds number is off, then the fluctuating components are a little bit off. Yeah. So this is a very caveat. Only works to a certain point. Yeah, it's subsonic, but to a certain point. And the testing that he found was approximately 0.5, and in some cases to 0.6. Yeah. Obviously, some further testing is required for this to show this, but this is what I know from the results that I've read. And yeah, this is finding free shear flows. Yeah, got a nice little plume. Yeah, it works fine. It's all great. However, this model totally falls apart. Yeah, I'm being nice here. It just goes kaboom in highly turbulent flows, okay, such as supersonic, hypersonic, yeah, and the testing he did, even in subsonic, high subsonic flows, it falls apart. In high streamline curvature, yeah, highly rotational flow, you find in turbo machinery like the Brayton cycle turbos and gas turbines and blah blah blah. Okay, it really falls apart. Also, this is a special case too, where flow separation and reattachment occurs. This is not a good. This actually is a bad model. There's a similar model. There's a basically you can't use the standard K omega model. You have to use you have to use an additional parameter for this. But anyway, that's not the point. For this, mu t doesn't like it. Yeah, very simply put. So, and now authors such as Cho and Rota, Hanjik and Lauder find this because the turbulent fluid behaves like an elastic. Yeah? Think of rubber band. So when you exert a force, when you exert a tensile force, it comes back on itself. First of all, that's not how fluid works. Yeah, if you add some tensile force, it should separate, not come back on itself. Yeah, so I think that's because it overpredicts the turbulent dynamic viscosity. Yeah. So the same authors introduced the Reynolds stress model. Yeah. Instead of simplifying this, they are literally solving this with a partial derivative, and it's a whole set of new equations. The equations are long, and it's not within the scope of this video. Okay. It's I've said it here. It adds a total of 6 equations. Yeah. It's crazy amount of equations you're solving. It's 3 times more than the K epsilon omega models. Mind-boggling, eh? Mind-boggling. So, and also the more equations you add, the more higher computational time. Yeah? This is why K epsilon omega models are very popular in universities. It's this almost, I would say, mass consumerism with testing. You want to show what CFD is capable of, so K epsilon and K omega. The models are great, don't get me wrong. They're great for certain situations, but yeah, there's a real problem where highly turbulent flows, high Mach numbers. So you use this model, the RSM model, or the Reynolds stress model, in, like say, in aviation, when the Mach number is really, really high. Okay? And so like I said, we didn't simplify this, we're solving for this. Okay? But this means the RSM model is very accurate because it solves all the transport components. All. We're not simplifying. It solves all of them directly. So this is my reference list. So this is the original source from Joseph Boussinesq himself. It's written in French, so if you can speak French, go for it. Sorry, if you can read, read it, go for it. It's old French, so it's pretty hard to read. So, but this guy gave a good little, shall we say, summarization of this. So this is for like English speakers. You can understand English, and if you're French, please read this. It's I have my French buddy reading it, and he liked it because old French is quite nice to read. That's what he said. So just to iterate. I want to say this. I just want to iterate this. This is a very important parameter. Turbulence. It's turbulence. It's a turbulent property, and it's not a fluid property. It can change from one point to another, and is heavily affected by flow history. According to 3 and 4. Please remember this. Okay. Thank you very much for taking your time in my video. Really appreciate it. Thank you. Bye now.